Okay, in this part, we want to work on IMO 2023 problem 1, and it has two ideas that can be useful in SUMaC, Stanford University Mathematics Camp 2022. Problem 2, these problems can be solved with same background idea. Also, this problem of IMO, the ideas are what? Considering small example and ghost idea, or someone call it rainbow idea. So we want to learn these two ideas, then we can solve these three problems together. IMO problem 1, SUMaC problem 2, and IMO 1994 problem 1. After that, I will leave some homework for you that you can solve with similar ideas. USAMO 2023 problem number 3, which is last problem of first day. Problem 4 of IMO 2020. Again, you can solve it with considering a small example. This problem of IMO, this problem of USAMO, you can do these 1, 2, 3, 4 problems as homework at the end. So we work on the idea, we solve these 3 problems with the idea, and then I will leave homework. Okay. And if you had question, if you wanted more homework, if you wanted to learn more background ideas are so much important. If you want to learn more, as I said before, feel free to send message to my WhatsApp number in the description and comments. Consider a small example is to consider, for example, N1, N2. It's not hard, goes ideal. Let me explain this for you in with one problem. The problem says n is positive integer. What's the product of positive divisors of n? So let's see. For example, let's consider n is 1, the product is 1 and 2. It will be 1 times 2 is 2. And 3, it will be 1 times 3, 3. And we can continue. For example, let's consider larger numbers like 6. It is 1, 2, 3 times 6. So as you can see, 2 times 3 is 6, so you can say 6 squared. Let's consider, for example, n8. 1 times 2 times 3 times 4. Sorry, 1 times 2 times 4 times 8. Again, 2 times 4, 8, 8, 8. It's 8 squared. Now let's check, for example, n24. When we want to write divisors of 24, let's find first two divisors. When we write 1, we write 24. The product is 24. When we write 2, it is 12. When we write 3, it is 8. We write 4, it is what? 6. Okay. Now, let's see ghost idea means what. As you can see, 1 times 24, let me write with other color. 1 times 24 is 24. 2 times 12, 24. 3 times 8, 24. 4 times 6, 24. So, we can say the product is 1 times, and they say rainbow idea because of this. It looks like rainbow. 1 times 2 times 3 times 4 times 6 times 8 times 12 times 24. We can also write it in reverse order. We can write it as 24 times 12 times 8 times 6 times 4 times 3 times 2 times 1. And then we say, okay, let's calculate p squared. 1 times 24 is 24. 2 times 24 is 20. 2 times 12, 24. 3 times 8, 24. 4 times 6, 24. 4 times 6 again, 24. 3 times 8, 24. 12 times 2, 24. 24 times 1, 24. So it will be 24 to the power of 1, 2, 3, 4, 5, 6, 7, 8 number of positive divisors. And then we raise the power of 1/2, or we take square roots. So product equal to 24 to the 8 over 2. It is 24 to the 4. So for general n, if t equal to number of positive divisors of n, then we can say product of positive divisors equal to n to t over 2. Why? We can prove it easily because again we say, okay, suppose the divisors are d1, d2 to dk, and we know the first one is 1, the last one is n. We know when d is a divisor, n over d is a divisor, and the proof is easy. You can prove it as homework, and if you have question, let me know through WhatsApp. My WhatsApp number in the description and comments like this. When we have 2, 24 over 2, 12 is divisors. So here, when we write it in reverse order, dk minus 1 times d1, we know that when d1 is less than d2 less than to dn, dk, n over d1, here if I want to write it, I write n over d1 is what? Is greater than n over d2. It's greater than n over dk. So this one is what? This one is dk. It is in reverse order, d1. So when we write it like this, d1 times this is what? d1 times dk is n, like this. So we multiply it, and we can conclude p squared is what? d1 dk n times n times n. And we said, okay, k equal to t, number of positive divisor. It is equal to n to the t. Because k is number of positive divisor, we could also write instead of k here t. Because in the beginning we set t equal to number of positive divisors. So dt here, n d1, n dt, it is d1, it is dt, it is dt minus 1. So product of them is this, then you raise the power of 1/2, then p equal to n over t over 2. So your homework 1 is to prove this. Let me explain completely. Homework 1 is what? D divides n. Prove that n over d also divides n. It is obvious, and as I said, if you had question, you can send message to my WhatsApp number in the description and comments. Close idea we've covered. Considering a small example, it's obvious we should check small cases like this in the problem. We will work on that. Now, let's try to solve this problem of IMO, then SUMaC, and then this IMO problem with Gauss idea. And in each part, you can pause the video and try on your own to improve your problem solving. So let's try first this problem of IMO 2023. Okay. It says determine all composite numbers n greater than 1 that satisfy the following property. If d1, d2 to dk are all the positive divisors of n with 1 equal to d1 less than d2, 2 less than dk equal to n, then di divides di plus 1 plus di plus 2 for every I from 1 to k minus 2. Why it says composite? Because we need at least 3 divisors to check this. For example, d1 divides d2 plus d3. If it is not composite, it's prime or it's 1. So we have at most 2 divisors. And we can check this condition. That's the reason the problem says composite. And only I wanted to tell you why. Now let's check a small example. The first composite number is what? 1, 2, 3, 4. Let's write the divisors. 1, 2, 4. The only condition we should check 1 should divide 2 plus 4, which is correct. So n4 is the first answer we found. The next one is what? n6. 5 is prime, 6 is composite. 1, 2, 3, 6. Now, is 6 good or not? Good or bad? Good means satisfy the condition, bad doesn't satisfy the condition. So, here 6 is not good. Why? Because 2 should divide 3. 3 plus 6, 3 plus 6 is 9. So 2 doesn't divide 9. 9 is odd, 2 even, so it is bad, so n6 is bad. Let's check, for example, next composite number is 8. 1, 2, 4, 8. So 1 divides 2 plus 4, it's good. 2 divides 4 plus 8, it's good. Now, n8 is good. So n4, 8, good. So can we guess, for example, what numbers are good and then try to check? Yes, in first step, we can say powers of 2 are good. And we can generalize more and say powers of primes are good. And exactly in the problem of SUMaC, we should use same thing, this part. We should check primes first, then PQ, then P squared, power of primes, to understand the problem. Okay, so let's check. We check power of primes. If it was not correct, we check powers of 2. So suppose n, so our claim is what first? N equal to p to the alpha, which p is good prime. If n is this, then n is good. So let's check, is it correct or not? How we've understood this? By considering a small example. So let's prove it. The divisors are what? 1p, p squared, p cubed to p to the alpha. And we should prove why p to the I divides p to the I plus 1 plus p to the I plus 2. We should prove this. We know that p to the I divides p to the I plus 1. Why? Because it is p to the I times p. It is multiple of p to the I. Also, p to the I divides p to the I plus 2. You should know divisibility, all rules. If you have problem with rules of divisibility or want to learn more things, as I said before, feel free to send message to my WhatsApp number in the description comments. It is pi times p squared, so both of them are multiple of p, then we add. So pi divides pi plus 1 plus pi plus 2, and we proved this. So this claim is obviously correct. Now let's check some other numbers. N6 and 8 we've checked. What about n on? We've seen that. So claim 1, any good thing that we reach, we write it as a claim. And at the end, it's good, so much good for exam. If you couldn't prove the problem completely, you can write those claims quickly and write the proof. Then you can get some mark. It is so much important because, for example, you can solve 2-3 problems, then you can get some mark from each of them, then it will be equivalent to solve one more problem. So N6 was bad. We can guess which numbers are bad. PQ, power of 2 different primes. Let's check this as claim 2, is it correct or not? N equal to PQ, P is not Q, PQ are prime, and we want to prove N is bad. So let's prove it. Let's see, can we prove it? The divisors are what? Without loss of generality, suppose P is less than Q. So the divisors, if we write in increasing order, will be what? 1 PQ, PQ. Now I want to prove it by contradiction. So P divides Q plus PQ. We know P divides PQ. So if we subtract P divides Q, but we know that Q cannot be multiple of P because both of them are prime. The only divisors of Q are 1 and Q, and P is not Q, and P is not 1. So that's a contradiction. So we prove PQ are bad. So 4, 6, 8. The next number we can check is what? 9. 9 is power of prime. We proved that by claim 1 it's good. N equal to 10. It is PQ by claim 2, and 10 is bad. N 11 prime. We don't need to check that. 12. Let's check 12. So let me write this. The proof is completed here. Also this. N equal to 12. The divisors are what? 1, 2, 3, 4, 6, 12. So as you can see, 2 doesn't divide 3 plus 4. So that's bad. Now our claim is what? N equal to P squared Q. PQR prime. Look, I don't want to consider only solution, okay? I want to just consider the situation of exam. You're in the exam, you don't know the straightforward solution is what. You want to analyze the problem, consider different cases. Maybe some claims are not so much useful. It's not important. We check anything that we guess may be useful. And at the end, for example, we prove 10 claims, 9 claims, 6 claims, and we understand 4 of them are useful. It doesn't matter. But with this way, you can easily check a lot of things and reach the solution. So let's check. N equal to P squared Q. And the time of this exam, this problem is 1 hour and a half. You can work on this 1 hour and a half. But also by checking all these things, it takes at most 30 minutes. I'm explaining. But when you want to solve, you don't need to explain. Okay. N equal to p squared q, p, q are primes, p is not q. We want to prove n is bad. So let's prove it. Let's open some page. Okay, so let's check. Maybe p is smaller, maybe q is smaller. Okay, so we check. Suppose 1 is less than p, or maybe 1 is less than q. Here you cannot say without loss of generality, because the n is not symmetric with respect to p and q. Power of p is 2, the power of q is 1. After p, next one cannot be pq. Next one has to be q. Or p squared also. So let's check 1q. I write it here. 1p squared. But when you write q, because you don't have q squared, the next one has to be p. And I know that q divides p plus next one. Q first, for example, suppose it is x. We don't know x is what. Q divides p plus x. Q shouldn't divide x. If q divides x, then because of this, we conclude q divides p, which is contradiction. So this one cannot be multiple of q. So it has to be what? Has to be p squared. But let me tell you something. PQ in this case is smaller than p squared. Why? Because PQ is smaller than p squared. The reason is what? If you divide by p, q is less than p, and it's correct. So next one is not p squared, should be pq. So contradiction here. P is less than q, because p is smaller, p squared is less than pq. Here, p divides q plus p squared, p divides p squared. So if you subtract, p divides q. And again, that's a contradiction. One part is left, 1p squared. So the next one has to be pq. And the next, sorry. The next one has to be q. And here we know that some other things, p divides p squared plus q. Again, because p divides p squared, then if you subtract, p divides q. Again, contradiction. So for all parts, we've reached contradiction. And as you can see, for example, look, when we have p squared, because p divides some of the next twos, if these two things are multiple of p, this one is also multiple of p. Next one also multiple of p. Okay, so we've reached good things. So here we prove this claim. Now, during proving that, we reached two good things. Claim 4. If two consecutive numbers, for example, di plus 1, if both of them are multiple of p, if p divides this and p divides this, then we want to prove p divides di plus 2, all the numbers after that, di plus 2, di plus 3, to the end, dk. The reason is what? P divides di divides di plus 1 plus di plus 2. So by considering these two things, we conclude p divides di plus 1 plus di plus 2. And we know p divides di plus 1. So we conclude p divides di plus 2. Okay? And similarly, we've concluded di from di and di plus 1. We prove di plus 2 divides. Then similarly, we can say di plus 1, di plus 2, di plus 3, and go up to dk. It's similar to induction. Okay, we proved claim 4. Claim 5 also, we can say if p divides di and p divides di plus 2, then let me write p divides di plus 1, p divides di plus 3, di plus 4, and so on. Proof is similar to previous one. Again, we can say, okay, p divides di divides di plus 1 plus di plus 2. So p divides di plus 1, because p divides d. And we can say, because p divides di, and di divides this, we can say first p divides di plus 1 plus di plus 2. From assumption, we know p divides di plus 2. So if we subtract, p divides di plus 1. And because p divides di plus 1, then by claim 4, we can say it divides all elements after that. Okay, now we've considered these claims. So we've proved 12 is bad. Now that we've understood all numbers are bad except power of primes, we guess that, let's write it as claim 6, if n is not power of prime, n is bad. n is not power of the prime, and we know n is composite number. It's not prime, it's not 1. Then n is bad. Let's try to prove this lemma. So, because we can say n equal to what? P1 alpha 1, P2 alpha 2 to Pk alpha k. Because we have k, it's better to use new variable, for example, Pm alpha m. And we know that m is at least 2, because if m is 1, then it is power of prime. So we have P1 and P2. So the first divisor is 1 without loss of generality. Suppose P1 is less than P2 less than P3 to Pm. So the first one is P1. The next one maybe is P1 squared. Maybe is let me tell you something. If it is P1 squared, maybe it is P1 squared. Maybe it is what if P1 squared is not the number after that, it has to be P2. If it is P1 squared, then by claim 4, we said if two consecutive numbers are multiple, for example, prime, then all numbers after that are multiples of prime. But do you agree? We know that we reach P2 in some places, okay? So by claim 4, we conclude what? We can conclude that P1 divides P2, and that's a contradiction. So after P1, we have P2. Next one. This number cannot be multiple of P1. Why? Let's check these cases. So if it is multiple of P1, P1 times something, P1s. P1, maybe it is P1 squared. And let me say, if it is multiple of P1, it has to be only P1 squared, because P1 times something, the smallest one is P1 squared. But maybe alpha 1 is 1. Okay, so because I want to prove all of them with the same way, suppose it is P1s. Okay. Here we have P1s, or it is multiple of P2, P2r, or if it is not multiple of P1, not multiple of P2, it has to be P3. Okay. Now, in this part, let's see, and we should have P3. Why? If we don't have P3, then we have n equal to or n equal to P1, P2. Okay, otherwise we have this first case, second case, third case, fourth case, fifth case. We are considered. It has also another easier proof, but I just want to check exactly with the things we worked on and reached by considering a small example. So because it is P1s, P1 divides, this is multiple of P1, multiple of P1 by claim 5. We said if di is multiple of p, di plus 2 multiple of p, all other numbers are multiple of p. So p2 should be also multiple of p by claim 5. P1 divides p2, contradiction. Next part here. If it is multiple of P2, all numbers after here should be multiple of P2. So by claim 4, because all numbers after this should be multiple of P2, n equal to P1, P2 to alpha 2. Okay? Now, in this case, if I want to write divisors, let me open some space. Here it is fourth case. I can say 1, P1, P2, P1 was the smaller. The next one we don't know. For example, it is P1 squared times something or not. We said if it is multiple P1, we have problems. So it is what? P2 squared. And let's consider also last numbers, like ghost idea, rainbow idea. It will be P1, P2 alpha 2. We divide by P1, it will be P2 alpha 2 minus 1. And if we divide by P2, it will be P1, P2 alpha 2. Let's see. Here we divide by P1, so it will be P2 alpha 2. If we divide by P2, it will be P1, P2 alpha 2 minus 1. Okay. And now we know P1 divides P2 plus P2 squared. So one thing, P2 1 plus P2. Because P1 and P2 are relatively prime, we call it also Euclid's lemma. P1 divides 1 plus P2. Okay, we have this condition. Here we can say what P1, P2 alpha minus 1 divides P2 alpha 2. Here let's write alpha 2. And plus P1, P2 alpha 2. Okay. Now, P1 divides, so P1, because P1 divides this part, P1 divides this plus this, but this is multiple P1, so P1 divides P2 alpha 2. Because P1 is prime, P1 divides P2, and that's the contribution. Okay. So we've only worked on this part. Now next. If it is 1, P2, P3, again, let's consider last part. We can consider it is n over P, the last one is n over P1, n over P2. Again, if we use the same thing, we say n over P2 divides n over P1 plus n. Then we multiply it by P1, P2. So P1n divides n, P2 plus n, P1, P2. Okay. Now we can say n is what? N is P1 alpha 1, P2 alpha 2 to PM alpha n. Because of this, so when you multiply P1n, you know P1 alpha 1 plus 1 divides P1n. Because P1 alpha divides n, let's multiply by this. So we conclude that P1 alpha 1 plus 1 divides NP2 plus NP1 P2. Or let me tell you easier way. I can say this, then I say, okay, P1 alpha plus 1 divides this, but it doesn't divide this, that's contradiction. Or we can say P1n divides this one. So P1n divides NP2 if you subtract. Then we divide by n, P1 divides P2, and that's the contradiction. Okay, now we understand something. And NP1, P2 we proved by, I think, it was claim 2, claim 4. And claim 2. By claim 2, we proved it is valid. So we proved this and the problem has been solved. Now that we've reached these things, if you want to write the solution here, we understood Gauss idea is so much useful. So we can say what? We can say, okay, we consider 1, then D1, then D2. Then here we consider n over D1, n over D2. Then we say what? We say n over D2 divides n over D1 plus n. So if you multiply by D1, D2, n D1, nd divides n D2 plus n D1, D2. Now we know nd1 divides nd1 d2. So if you subtract nd1 divides what? nd2. So we conclude what? We conclude d1 divides d2. Okay? And then we can say what? d1 divides d2. Okay? We know d1 divides by assumption of the problem d2 plus d3. So n divides d3. Again, you can prove it by induction that, sorry, d1. D1 divides all numbers. Suppose n D1 is P, we know it's prime. And then we conclude P divides all other divisors. So we don't have any other prime because, for example, if you have Q, then P has to divide Q. Then, as you can see, we said P divides D1, P divides D2. Okay? So by claim 4, we can say P divides D3 up to all of them, DK. Okay? Because all of them are primes, so we don't have any other prime. Because if Q divides N, then we conclude P divides Q, and that's a contradiction. So we conclude that N has to be power of prime by claim 4. So here we understand claim 4 is important. And we proved why P to the alpha are good. It was, I think, the first claim. Yes, first claim. Okay. The proof of this problem was complete. Now, this problem of SUMaC, you can check my videos. I released a solution of this. I solved this problem exactly the same idea. Let me explain this problem for you. And if you had question, if you couldn't understand the solution, IELTS or wanted to learn more background ideas, anything, as I said before, feel free to send message to my WhatsApp number in the description and comments. So let's try this problem by using Gauss idea. So let's read. It says m and n be two positive integers, a1 to am be m different numbers from the set 1 to n, such that for any two indices with I less than or equal j less than or equal m, ai plus aj is at most n. And it says there exists, so it's a bit complicated, a lot of variables. So let's see. Problem says what there exists an index k such that ai plus ajk. And so it says such that for any two indices I and j that satisfy this, there exists k that ai plus aj equal to ak. Show that we have this. So when I want to prove this, I say, okay, I should prove a1 plus a2 to am. I want to see the problem from Gauss idea approach or rainbow idea approach. M times n plus 1 over 2. So I want to write it in reverse order, am plus am minus 1 plus a1. And then consider like this. If I say each of them at least what, then we can solve the problem. Look, suppose, for example, we prove each of them is at least t. So it is s, it is s. Then we want to prove this. Then we can prove 2s is at least mt. So then s is at least mt over 2. I want to prove why it is equal to why it is this. So look, these things are not necessarily correct. We want to see, we should prove around what? We understand that if t equal to n plus 1 over 2, then the problem will be solved. Okay? So now here, our it is not equivalent to the problem because maybe one of them is greater than, for example, 100, one of them greater than equal to. But if we prove a1 plus am is greater than equal n plus 1 over 2, a2 plus am minus 1 greater than equal n plus 1 over 2, and in general, ar plus am plus 1 minus r greater than n plus 1 over 2. If we prove these things, the problem will be solved. Okay, and last part will be am plus a1 greater than equal n plus 1 over 2. We should prove these things. Now, here again, if I want to prove, I can prove this for general in first step, but it's not good. It's good to try to solve this with considering a small example. Considering a small example, it means instead of general R, we try to prove A1 plus AM, then A2 plus AM minus 1, find the idea, and then try to prove AR. And for your answer sheet, you can only write for AR, but for yourself to understand problem better, to reach the solution, it's good to use considering a small example. So, as I said, sometimes from the beginning, it's not good to use a small example. You can try, but you should also pay attention during the solution. In some part, again, you should use a small example, okay? Because it is so much powerful and helpful. Let's prove a1 plus am is greater than equal to this. I want to prove this. Let's see the condition of the problem. We know ai are different numbers, and we want to prove, one thing, sorry. mt over 2 is this, it will be n plus 1. Let me correct all these parts, n plus 1, n plus 1, n plus 1, n plus 1. Because when mt over 2 is m times n plus 1 over 2, you can cancel 2 and m, and t should be equal to n plus 1. So let's try to prove. I want to prove this. I prove it by contradiction. Suppose a1 plus am is at most n. So by assumption of the problem, it is equal to ak. Okay, so a1 plus am, we know what, and let me tell you something. In the beginning, we can say without loss of generality, there are different numbers. We can consider a1 is strictly less than a2 to strictly less than am. Now, a1 plus am equal to an is less than or equal to n, so by assumption of the problem, a1 plus am equal to ak. For example, something, ak. But we know that am is greater than all of them. Okay, so am plus a1, and also there are positive integers. Okay, we know ak is at most am. because AM is the largest one, and equality holds when K equal to M. It is at most AM, and if we cancel, then we reach A1 is at least 0, at most 0. So it's a contradiction because they should be positive. So we see that the first part is so much easy, it doesn't help so much for generalizing that. Because in a small example, the first cases are so much easy. We should continue for 2, 3, then we can generalize that. Now, A2 plus AM, again, we use contradiction. AM minus 1 is at most N. So A2 plus AM minus 1, by assumption of the problem, it is again equal to, for example, AKA something, AL. And we know, because AM minus 1, A2 plus this is greater than AM minus 1, the only possible case is AM. So it has to be AM. Now, if we consider A1 plus AM minus 1, because it is less than or equal N, and A1 is less than A2, so A1 plus AM minus 1 also is at most M, because A1 is less than A2. So A1 plus AM minus 1 also should be equal to, for example, AL prime. Again, for this one, the only possible case is AM, because it should be greater than AM minus 1, and the only possible case is AM. It is equal AM, so this part equal to this part. And if we cancel AM minus 1, A1 equal to A2, but the problem says they are different. Now it's a bit better for generalizing. Let's check one more. After A3, we generalize this part. Why A3 plus AM minus 1 is at most N plus 1? Again, we use contradiction. We say, okay, A3 plus AM minus 1 is at most N because they are integers, and when it is less than N plus 1, it is at most N. So A3 plus AM minus 1 is at most N. We decrease it. A2 plus AM minus 1 also will be at most N because A2 less than A3. A1 plus AM minus 1 also at most N. And if we consider the problem, the condition, then we conclude from this part. A3 plus AM minus 1 should be AL1. A3 plus, A3 plus AM minus 2 we should prove. So let me correct these indices. A3 plus AM minus 2. AM minus 2, AM minus 2, AM minus 2. A3 plus AM minus 2 this. A2 plus AM minus 2 equal to AL2. A1 plus AM minus 2 equal to AL3. Now, as you can see, because A1 is less than A2 less than A3, so AL, and in all of them we have AM minus 2, so AL3 is less than AL2 less than AL1. Okay? But as you can see, these numbers should be greater than AM minus 2. Because we have here AM minus 2 plus a positive number. So they can be only what? AM minus 1 AM. So we want 3 different numbers from this set that has 2 elements, so that's a contradiction. Now we are ready to generalize it with exactly this idea. So let's prove for AR. I want to prove with contradiction. So AR plus AM plus 1 minus R is less than or equal N. So I can say AR plus AM plus on. Because of this, we can say, okay, AR minus 1 plus also AM plus 1 minus R. We decrease it by 1. It is at most N up to A1 plus AM plus 1 minus R is at most N. So this part plus 1 minus R equal to ALR, let's say, for example, let's say AJR. This part AR minus 1 plus AM plus 1 minus R equal to AJR minus 1 up to A1 plus AM plus 1 minus R by assumption of the problem, because it is at most N, equal to AJ1. And we know because A1 is less than A2 to AR, so we conclude AJ1 is less than AJ2, less than to AJR. And we know what? Because all of them are AM plus 1 minus R plus a positive number, we know they are greater than AM plus 1 minus R. So they can be belongs to what? AM plus 2 minus R, AM plus 3 minus R, to A what? AN. And here we have 3 elements, 2 elements. We should consider we have R elements here. It should be, and last one is AM. We should have what? We should have R minus 1 elements here to reach contradiction. How many elements are here? m minus last one minus first one plus 1. So it will be m will be cancelled. It will be r minus 2 plus 1, which r minus 1 element. But we need r different elements here, so that's a contradiction. So in general, we proved all of them are at least n plus 1. We proved all these question marks. We proved for general r. So because there are at least r plus 1 with ghost idea or rainbow idea, we proved this problem and we proved the sentence of the problem. And as I said, as homework, we had one homework one during the video. This one is easy. Try to solve this homework too. You can use small examples to solve last USAMO, the most prestigious national exam. In Olympiad homework 3, this IMO problem, again with considering small examples. Homework 4 and homework 5. Okay, so if you want to learn other background ideas and solve similar problems and had question about the homeworks or the problem or the idea, as I said before, and want to prepare for important summer camps, as I said before, feel free to send message to my WhatsApp number in the description comments. Thanks.